Welcome to a screencast on an introduction to chemical moles. If you were a cook or a baker making food for lots and lots of people, you would certainly order something like eggs, not by how many individual eggs you needed, but by how many dozens of eggs you needed. And if you were an office manager, you wouldn't order how many sheets of paper you needed. You'd order paper by the ream or possibly by the box. And things like a dozen, which means 12 of course, or a ream, there's 500 pages in a ream of paper, those are useful quantities for these sorts of situations. Now, chemists of course deal with matter, the substance that makes up our world, and even very small quantities of matter, like this tiny droplet of water, contain tremendously large numbers of the particles that make it up, in this case water molecules. And because of this, chemists use a unit somewhat analogous to a dozen, and it's called the mole. Now, a dozen always means 12. You have 12 eggs, or a dozen eggs, that's 12 eggs. You have a dozen horses, that's 12 horses. And a mole is also a number of things, but it's a much, much bigger number. 1 mole of anything is 6.022 times 10 to the 23rd of those things, whatever they are. This is kind of like the chemist's dozen. Now, of course, you're typically not going to count out individual atoms or molecules or ions. We typically weigh things out, and the mole has another meaning, and the mass of a mole of any element or of any compound can be determined from atomic masses, and those are of course found on the periodic table. Now, one other thing to note, this really, really large number, 6.022 times 10 to the 23rd, is also called Avogadro's number, and here it's symbolized by n sub a. N stands for number, the subscript a stands for Avogadro, and the definition of Avogadro's number is how many atoms of the isotope carbon-12 are in exactly 12 grams of carbon-12. So if we were able to pile carbon-12 atoms, only the isotope carbon-12, on a scale and get it up to exactly 12 grams and then count how many atoms we have, what we would end up with is a really, 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 really large number, and it's exactly, to a lot of significant figures, 6.022, 14129 times 10 to the 23rd, and we'll usually just use 6.02 or 6.022 times 10 to the 23rd for the Avogadro constant or Avogadro's number. Now, this is usually easiest to deal with by example when starting. So let's say that we have 1 mole of copper. Just as a note, mole, M-O-L-E, our abbreviation for that is MOL. So 1 mole of copper, how many atoms is that and how many grams is it? Well, since it's a mole, it's 6.022 times 10 to the 23rd of those things. Just like if it was a dozen, it would be 12. So 1 mole of copper is 6.022 times 10 to the 23rd copper atoms. And then the periodic table is useful because if you look where copper is on the periodic table and then look at its atomic mass, that is the mass in grams of 1 mole, or 6.022 times 10 to the 23rd, copper atoms. So notice that the 63.55 is the average atomic mass of the naturally occurring isotopes of copper, and in AMU, it's the average mass of 1 atom, and in grams, it's the total mass of a mole of atoms. Just for some perspective, a mole of copper is about 22 of the old pennies, the pre-1983 pennies that were pure copper. And if you weighed that, if you had 1 mole of copper, you'd get about 63.55 or so grams. And if you were able to zoom in and count the atoms, you would end up with this 6.022 times 10 to the 23rd atoms, this huge, huge, huge number. Okay, second example. What if we don't have exactly 1 mole and we wanted either grams or atoms? Well, in this case, we have 0.0463 moles of krypton, and we'd like to know how many grams we have. And this is a conversion problem. But we're going to now be using the periodic table to get our information. So, usual conversion problem method, we start with the known quantity. We look for a conversion factor that will cancel out the unit that we're starting with and want to get rid of. So, moles will go on the bottom of our conversion factor. And then on the top, we need to know what the mass is. So we look on the periodic table. For krypton, the mass of 1 mole is 83.80 grams. So that goes on top. We do the math, cancel out the units, and 0.0463 times 83.80 gives us 3.88 grams of krypton. That's the mass that corresponds to that number of moles. What if we wanted atoms? Well, in this case, we actually don't need the periodic table, but we do the same type of process. We start with the known number of moles of krypton. We look for a conversion factor that converts from what we have, moles of krypton, to what we want, which is krypton atoms. And if it's a mole, it contains 6.022 times 10 to the 23rd particles. And in this case, the particles are krypton atoms. So we do our math. 0.0463 times 6.022 times 10 to the 23rd, do our unit cancellation, and we get 2.79 times 10 to the 22nd krypton atoms. So notice we have two ways of looking at the amounts, number of moles of krypton, how many grams it is, or how many atoms it is. Okay, let's do one the other direction. 2.465 grams of copper. How many moles of copper is that? Well, we start with what we know. We look up the atomic mass, which we've used previously. This time we're canceling grams, so the mass goes on the bottom and the moles goes on the top of our conversion factor. And 2.465 divided by 63.55 gives us 0.03879 moles of copper that mass is equivalent to. Now, what if instead we were trying to find number of copper atoms, starting with grams? Well, if this was the only problem we had, to convert from grams into number of atoms, we'd have to first convert from grams to moles and then from moles to atoms. But we've already done the grams to moles conversion, so let's just continue from there. We have 0.03879 moles of copper. Our conversion factor is 1 mole of copper contains 6.022 times 10 to the 23rd copper atoms. Cancel units, do the math, and we get 2.336 times 10 to the 22nd copper atoms. Now note, this mole concept, this mole idea, is very useful in lots and lots of chemistry situations. It's going to help us determine the formula of a compound and determining all exact amounts of substances that react or are produced during a chemical reaction, and lots more. So you have to get to where you're pretty able to do certainly the basic calculations and conversions readily. And that's it for Introduction to Chemical Moles.